Thank you. Thanks both for the introduction and the opportunity to speak here. I want to talk today about a particular aspect of my work. I study groups acting on manifolds in low dimensions and higher dimensions. I'm going to talk today about a very particular approach to the problem of groups acting on the circle. And I like this avenue because it relates to problems both in algebra, like purely in algebra about structure of groups, problems from geometry and topology and geometrically motivated examples, and from dynamics of group actions. So hopefully there's a little something of for everyone in here. And if nothing else, the definitions to get you into this subject are pretty easy to state, and you can sort of start playing around with them right away. So let me start with a purely abstract algebraic definition. My talk is called something about orderable groups. Let me tell you what an order on a group is. So left invariant linear order, which I'll just abbreviate to LO for left invariant linear order on a group G is, well, it's exactly what you might expect. It's a total order that's invariant under left multiplication. So such that if I have A less than B elements in my group and C is another element of my group, if I left multiply, I preserve the inequality. Okay, so this is just an abstract extra algebraic condition you can put on a group. What are some examples? Here's an easy example. You could take the integers as an additive group with the usual order. Great. We all learned in, I don't know, kindergarten that this is, or maybe a little after kindergarten, that this is how adding numbers works. Maybe more interesting, there's your usual order. More interesting than this, you could take pairs of integers, again as the additive group, and you could take the lexicographic order where you compare the first coordinate first and then the second. And if you want, as a little exercise or a challenge, this was maybe an obvious thing to do on this group, but not far from the only one. You can actually find infinitely many, actually uncountably many, different left invariant total linear orders on Z cross Z. Okay. And actually, you can kind of parameterize this nicely with a Cantor set worth of them. Okay. So if you lose your train of thought during my talk and want to do a little math problem, solve this exercise. Okay. Oh, maybe I should give you a non-example. Not every group admits one or many of these. Any group with torsion, with a finite order element, will fail to have this. For example, if, I don't know, some element in your group satisfies a power of it, let's say, I don't know, G cubed is the identity, then this will break right away, right? I'm supposed to say that identity is either going to be bigger or less than G. Maybe it's less than G. I can multiply this by G. I'll get G is less than G squared. And if I multiply this by G again, I'll get G squared is less than G cubed. But wait, G cubed is the identity, and this contradicts one of the axioms for a total order. So this can't possibly happen. But there's much more subtle obstructions, and there are many examples of torsion-free discrete groups, finitely generated groups even, that fail to admit left invariant orders. and actually we don't totally understand the whole theory. Okay. The historical interest in this subject, as you might guess from the way that I presented it, was purely algebraic. So this is just an extra algebraic structure you can put on your group, and there's sort of a family of theorems of the form either, if G has a left invariant order, then it has particular other properties, or if G has some nice properties, then you're guaranteed one of these orders. So sample theorems, here's one of the second variety. If G is a torsion-free nilpotent group, then it admits a left invariant linear order. That's a result of Malsav. Or in the other direction, if G has a left invariant linear order, then this extra structure lets you prove some things about the group. These are all examples of groups that satisfy a still open question, the zero divisor conjecture of Kaplansky. So then it satisfies Kaplansky's zero divisor conjecture. If you don't know what that is, that's not important, or ask me later. This is an important question in group theory, and left orderable groups are good candidates to, or they, it's solved for this big class. But I'm more interested, less in the algebraic questions, but in the modern interest in this. So really in the past, 10 or 20 years, there's been a resurgence of interest in studying these groups that comes from their connections with other areas of mathematics. So one of the most important connections here is, well, actually, let me start in order. One we'll see later on in the talk. So this will come later in the talk, not too much later, is the relationship with dynamics of groups acting on one-dimensional manifolds. Okay, so we'll see pretty soon how this plays out. So that if you do low-dimensional dynamics, this algebraic construction gives you a useful tool. I think what really prompted people to look at this again is interesting examples of new orders coming from geometric topology. Okay. So there's a wide class of things. We know that, say, fundamental groups of surfaces are left orderable, and there's particular orders that you can construct using some knowledge we have coming from geometric structures. Braid groups are left orderable, and there was originally a very algebraic proof of this that's quite difficult, but a much conceptually simpler one, a kind of geometric proof. There's a whole connection to foliation theory. Let me state a sample theorem. So this comes from work of Thurston, Caligari, more recently Steve Boyer, and many others. Okay. So let me state a sample theorem here. The theorem says that if you have a three-manifold with a particularly nice foliation on it, so a particularly nice way of dividing it up into two-dimensional subsets, then the fundamental group of that manifold has a left invariant linear order. So failure to admit one of these things, and in fact the failure to admit a left order is something that you can actually algorithmically check with a computer from a group presentation. Failure to that gives a significant topological obstruction to having a particular topological structure on your manifold. So the theorem, precisely stated, is that if you have nice, well, I'll state it a little bit loosely because it's not important to the talk. If you have a 3 manifold that admits what's called an R-covered foliation, then its fundamental group is left orderable. So it admits one of these left invariant linear orders. And the consequence of this gave some of the first examples of simple 3 manifolds that sort of failed to admit foliations of this type. Failed to admit particularly nice foliations. And maybe a third thing that I might as well mention, because this will also play out in the talk. So 1 is dynamics, 2 is geometric topology, and 3 is both of these sort of have led to new approaches to purely algebraic questions. New approaches to algebraic questions by studying a kind of a geometric dynamical picture where we consider the whole space of possible, or the whole set of possible orders on a group. So on a given group G. Okay, so what I want to do in this talk is kind of paint a picture of a little bit of 1, 2, and 3, or you know, how I got interested in this and what we're able to do with this modern approach. Okay. But first I want to step back a little bit and advertise a more general concept. I think from all of these perspectives, it's more natural. So I claim from all perspectives above, 1, 2, and 3, it's actually more natural to study a slightly more general concept called a circular order. Okay. So I don't know, for instance, if you're interested in kind of the geometric topology thing, you can prove much better results about fundamental groups of manifolds that admit circular orders. These arise from a much more general class. Our color-covered foliations are a pretty restrictive class of things. If you have something called a taut lamination, a taut essential lamination, then the fundamental group of your manifold will be circularly orderable. So from this perspective, it's more natural. From the groups acting on one manifold, you might guess that if this is like a linear order in the line, the circular one is about the circle. But before I get into that, I should just define what a circular order is. Okay. I want to imitate the definition of linear order for, well, instead of my total order being modeled off of the real points on the real line, I want to model it on the circle. So circular order on a group G is, so let's see what this should be. if my model space is the circle, it really doesn't make sense on the circle to say some point, x is less than y, because what's less than? But it does make sense to say that a triple of points, x, y, z, an ordered triple is either positively oriented, x, y, z, or negatively oriented if it was x, y, and z over here. So a circular order will try and capture this idea of orientation by giving a kind of a sign to distinct ordered triples. So it's a function, C, I'll call it, from your group, from triples in your group, to plus or minus 1 for orientation, and I'll allow 0 to capture a degenerate triple like XXY. Okay. So I'll require it to be 0 only on degenerate triples. Okay. Like the linear order, I have a group, not just a set, so I want it to respect the group multiplication. I require this to satisfy C of G1, G2, G3 is equal to is equal to C times, I don't know, HG1, HG2, HG3 for all G1, G2, G3, and H in your group. And if you go back to the circle and you think about if there's any other constraints satisfied by the ordering of points, suppose I take an x, y, and z that are positively oriented. So I know that C of x, y, and z is 1, say. Okay. If I want to place a fourth point, that's distinct from all of these, I have exactly 3 options of where to place it combinatorially. So I don't know, maybe I'm trying to put W here. So that would give me 3 options for an extra point. But I have many options a priori without any further constraints of my choices of, say, C, X, Y, and W are C, X, Z, and W, and C, Y, Z, and W. I don't just have 3 choices of location for W. I have 2 times 2 times 2. I have 8 choices of ways to assign this plus or minus 1. Right? That's definitely more than I have options for placing this. So there must be something else satisfied. And with points on the circle, they exactly, you could check, satisfy this cocycle condition where the alternating sum of these is 0. Okay, you can check that. There's a nice little geometric proof that works. Okay?
When you say degenerate triple, do you mean all of the 3 things are distinct? Or?
Yeah, at least 2 coincide.
Oh, okay.
Yeah. So on the fact diagonal. No. So a degenerate triple is example X, X, Y.
Okay, I see.
Yeah. I don't know how to assign an order to a pair. Yeah.
That's fine.
Yeah. Okay. This is not my definition. I don't know actually who made it up originally. It appears in some work of Thurston. It appears in much older work of some Russian authors who are considering something actually a little more restrictive than just left multiplication and variance. It's a pretty natural concept to think about. Okay. So that's a definition. Let's do some examples. What kind of groups admit circular orders? Well, if G, you would hope if G is the circle, then it admits a circular order. In fact, that's true. The usual orientation cocycle sort of function on triples of points in the circle gives you a left invariant circular order. Right? It's invariant under rotations orientation. So that's a nice example. So C equals usual orientation. More generally, if G acts by homeomorphisms on the circle, and say some that preserves orientations. So orientation preserving homeomorphisms on the circle, and let's say suppose some point X has trivial stabilizer. Okay. Well, then I can identify elements of my group with their the image of X under that element. So I can identify group elements with the orbit of this point. Okay. And this gives me an identification of my group with a subset of the circle. Okay. And I can look at the orientation of cocycle on triples of these points. Okay. And that will give me a circular order on my group. Okay. So more precisely, C of G1, G2, G3, if these are group elements, is the orientation of G1x, G2x, G3x. So this would be a huge class of groups that have circular orders. Oh, and one more sort of example. I advertised this. I was like, hey, it's more natural to study this more general concept. Here is why it's just a strictly more general concept. If G has a linear order, left invariant linear order, then it automatically has at least one left invariant circular order. All right, and here's the proof. If you know how to linearly order points in your group, okay, so you know what's less than what, then you know how to give an orientation of a triple by bending your line around like this. I know which way is greater and less. And now I know, I just pretend this is the circle minus a point. And you've got a orientation cocycle that's invariant under left multiplication. Okay, so you can formalize that into an actual proof. It really does work like this. Okay, so let me go back to dynamics and how this plays into the actual research that I do. The starting point is this kind of a folklore theorem. That says sort of that example 2 here is really all that's ever going on. Okay. Okay. So for countable groups, G admits a circular order, this purely algebraic construct, if and only if G acts faithfully on the circle by orientation preserving homeomorphisms. So G embeds as a group into the group of homeomorphisms of the circle. Okay. So in some sense, these are essentially the only examples. Moreover, for each circular order C on your group G, there's a canonical way to put G in this group. There is a canonical up to conjugacy. So up to conjugacy by some homeomorphism. Faithful representation of your group into homeo of the circle. So let's call it rho sub C because it depends on your order. And this canonical one comes along with a special point that has trivial stabilizer. So if you do this construction from up there, you recover exactly your circular order. So I'll say together with base point xc in S1, so that if I apply this construction, let's call it star, so that doing this construction to your action recovers the circular order. And let me just prove this moreover part, because I think it gives you a really nice handle on how to think about these things. So we can forget about linear orders for the moment. They've been subsumed by circular orders. They have a bigger playground to play in. Okay, so here's the proof, or at least a sketch of the moreover. Okay, so I'm given circular order C on some countable group G, and I want to build an action of this group on the circle in some kind of canonical way. So I have a countable group. I'm going to start by enumerating it. Let's start with identity is G1, and then do whatever you want. Just enumerate it somehow. Okay. And I'm going to embed my group in the circle using my order. So in a way that respects the order, and I'll just do this kind of inductively. I'll take my first point, that's identity, and I'll just put it wherever I want. Great. Now I'll take the next one, and I'll also put it wherever I want. Great, G2 goes there. And now get to my third point, and I know that the triple G1, G2, G3 is either positively or negatively oriented according to G, according to my circular order. And if it's positive, I'll put it in the midpoint of this interval. And if it's negative, I'll put it in the midpoint of this interval. So maybe if C, G1, G2, G3 is 1, I'll put G3 right here. Okay, and then I continue, I look at the fourth point, the fourth element of my group. The co-cycle condition says it can only be in exactly one of these complementary intervals, whichever one it's supposed to be in. As I look at all these ordered triples, I'll just put it at the midpoint there. Okay, continue. Okay. So the fact that this is a reasonable procedure comes from this condition here. Okay. Okay, so now, Gx on itself, which I've now identified with a subset of the circle by left multiplication. Okay, so preserving the n and preserving the order. And the fact that I chose midpoints actually means that you extend to a homeomorphism of this subset of S1. Okay. I did kind of a canonical thing. And you check that this is an action by homeomorphisms on some G invariant subset of the circle. And now you can just extend this to the rest of the circle in a canonical way. There's a canonical extension to the closure of this set. And then complementary regions of the closure are intervals that should be permuted by the group. And I can just send an interval to another one, another complementary interval, by, say, the unique affine map. Okay? So you extend this to the closure of my embedding in S1, then to all of S1, and you check that there's a canonical way to do this just by homeomorphisms. Okay. And if I want to recover the order, well, remember G1 was the identity, right? I should just call this point XC, my base point. Okay. And then these things really are its image under particular elements of my group. And I'll recover exactly the order. Okay, so that was kind of a sketchy sketch, but that's really the outline of the proof and how it goes. It's quite concrete. The things to check at the end is that I made a lot of choices, right? I enumerated my group. That was a choice of enumeration. I put the first point and the second point somewhere haphazardly. And you have to check that the construction you get only changes by a conjugacy of this, by a homeomorphism if you change these parameters. Okay. So check that this is well defined.
So this construction, you are saying that using star, so does it have this point where the G is at?
Yeah, the point is the point that I labeled by the identity element of my group. And this will have trivial stabilizer. Its orbit is just the group elements. And if I want to know, the image of this under G3, well, identity times G3 is G3. There we go. Yeah. So you really do get a base point along with this construction.
Then,
Yeah.
you said actually the cosine relationship. Just asking my question, whether there is any kind of way to describe this fraction of circular orders in the cohomology with the G-mass equation?
Yeah, this is a great question. And no, because this is a Z cocycle condition. I really don't want to sum these and then go mod 3. I really want this to be 0, not 3. But this is a homogeneous this is an inhomogeneous 2 cocycle on my group, right? There's a way to think of it like that. So you can think of this as an element of H2G with Z coefficients, but the coefficients happen to only take special values. And an interesting question is, okay, maybe I understand the second cohomology of my group. When is there a cocycle representative that only takes the values plus, minus 1, and 0? And 0, in fact, only on degenerate triples. Yeah, so understanding the difference between circular orders and group cohomology is actually a subtle and interesting question. Yeah. Okay. But actually, in particular, if you know something like your group has no second cohomology, then you can conclude that all circular orders happen to be linear orders. Right? So there are things you can do. Okay. But let me summarize what we get out of this board. Or out of the folklore theorem, generally. If you fix some group G, then there is a relationship, right? That if I look, let's call CO of G the set of all circular orders on the group G. There's a map from this space to the group of homomorphisms of G into homeo of the circle, actions of G on the circle, which this is rho maps to, this is C maps to rho C from this construction. Okay, and it kind of has an inverse on a specific set, right? If you take some point of if some action has a point with trivial stabilizer, Okay, there's a way to go backwards from star and recover a circular order. Okay. And this space for specific examples of groups is something I've been trying to understand for a long time. This you can think if G is the fundamental group of another manifold, this is the space of flat circle bundles over that manifold. It's a remarkably rich and hard to understand space, even if something like G is the fundamental group of a surface. And that's something I'll talk about in the lectures I'll give tomorrow and next week. This has been a mystery. Even like classifying connected components of this space in basic examples is hard to do. So I kind of got very interested in studying this map because, well, look, here's something that's purely algebraic, and here's a way to probe this space with something else. Conversely, in some examples, we understand this space pretty well. You might want to see if we can use this to understand circular orders on a group and answer purely algebraic questions. Okay. But for all of that, if I'm interested in this, I keep saying space, right? Calling this a space of foliated circle bundles or a space of actions. Two things are close, right? If generators of your group, say, go to close by homeomorphisms. We would want some topological correspondence to answer any of these questions at all. So first we should topologize this. This actually has a very natural topology where two circular orders are close if they agree, if they give the same value to large finite sets of elements. It's really just the space on this as a subset of the space of functions from triples to a set with 3 elements. And with that topology, it's easy to see that it's compact, totally disconnected, and provided your group is countable, it's metrizable. So this is actually kind of like a reasonable looking space. It looks like a sort of a subset of a Cantor set. And in some examples, it's actually pretty reasonable to get a hand on. So, for example, I don't know, let's do an easy example. If I take a group, the cyclic group with 3 elements, what's the space of circular orders on this group? Anyone want to do this computation?
What is that? 2?
Yeah, it's 2 points. It's exactly 2 points. So this is just some set with 2 points. Okay, there's this one, and then there's this one. If you take an infinite cyclic group, here's a harder exercise. The space of circular orders on this group is homeomorphic to a Cantor set. We know lots of other examples where you have groups where the space of circular orders is homeomorphic to a Cantor set. And maybe generalizing this, the state of the art here is we actually have a classification of all groups where this is finite. And that was some work that I did a couple years ago with Adam Clay and Cristobal Rivas. Okay. So we have a good kind of, there's a structure theorem for these groups. They all happen to be solvable in particular. We have a kind of a good understanding of what it means for this space to be finite. So I'm getting optimistic about being like, oh, look, this is, we know pretty well, let's use this to probe that. But unfortunately, this is too optimistic. If I take another like very basic example of group from group theory, how about like a free group on 2 generators? Not free abelian, a free group. Then I have no idea what this space looks like at all. Beyond that it's compact, totally disconnected, and metrizable. I'll tell you another fact by the end, but I can't say it's homeomorphic to like anything at all. Okay, so now we back up and you say, oh, okay, if you want to understand this, maybe it's better to understand this side and go backwards. Okay. Okay, so what's the hope here? Is that this summary picture is some kind of topological correspondence, so that topology here, where I understand it, can inform my understanding of actions, spaces of actions, of rigidity, foliations. Or where I don't understand it, maybe understanding this might help me go backwards and understand the space of orders. So hope is that this arrow and this, like, not really an arrow, but there's sometimes a way to go backwards, gives any kind of topological correspondence. Mm-hmm. And for a bunch of the next, probably the rest of the talk, I want to talk about some work I did with Cristobal Rivas that sort of kickstarted a bunch of these projects. Towards the direction of yes, there is some hard to pin down, not precise. Of course, these spaces can't be homeomorphic. This typically has very large connected components. This is totally disconnected. But there's something that you can say. Mm-hmm. We have precise statements and theorems towards a positive answer to describing this correspondence. Okay. So, for example, here's a little lemma. Okay, is that this correspondence that takes a circular order and assigns this canonical action up to conjugacy, this is continuous. Okay. So precisely, I guess this is not well defined as a map up to here. You're defined as a map up to conjugacy. So up to a conjugation action of that group. But this one is continuous, and in fact, if I don't want to take this nasty quotient, you give me, I don't know, a sequence that limits somewhere, you can find a sequence of actions that also converges to a particular action. So there's a way to do this, even making continuous choices. Okay, so that's some evidence that there's some kind of topological correspondence. Let's be a little bolder and try and conjecture something about a global correspondence between these spaces. Okay. The first thing you might want to know about a space like this, a compact, totally disconnected metrizable space with no isolated points, theorem, fact, exercise in undergraduate topology, no isolated points means it's homeomorphic to a Cantor set. So in fact, the easiest way to prove this is to show that there's no isolated circular order in this topology on an infinite cyclic group. So that's our first pressing question. When does this have no isolated points? Okay, so maybe let's naively conjecture or question. Circular orders on a group has no isolated points. That should correspond to something like, well, this is like as connected as you can be while you're still a disconnected space, right? You can perturb things always. That should be something like this space is maybe connected. Or maybe this is too much to look at. Maybe instead of this, you would want to instead say that, I don't know, the subset of faithful actions is connected. Okay, that's kind of the image of this map. You have a faithful action if you admit a circular order. Okay, so that's actually a reasonable first guess. Or a hopeful statement. And I got excited about working on this problem from a specific instance of this conjecture. That comes from close to home here. It was a paper of Professor Beck along with Eric Samperton from 3 years ago. They conjectured and gave some good evidence for. I'll state a specific instance of their conjecture. They conjectured that the space of circular orders on a free group of 2 generators has no isolated points. Okay. And this fits in line with this because Hom F2 homeo S1, you send the 2 generators wherever you want. This is actually homeo S1 cross homeo S1. That's a connected space. And in fact, with some work, you can show even that the subset of faithful actions in here, if you take G equals F2, is connected. So great candidate for this thing. We also know the space of left orders on a free group is connected. It has no isolated points. So this seems very promising. And I read this paper and I was completely convinced that this should be true, and I thought I should prove it, and got very enthusiastic. And then of course you work at this for a long time, and after a lot of sweat, I broke mathematics and found a counterexample. So theorem, which just shows that the situation is a lot more subtle than you think. So here's one thing we can say, is that the space of circular orders on the free group actually has infinitely many. Okay, so this is a crazily different than we expected isolated points. Okay, and so at this point I was sort of too embarrassed. I was sure I must have made a mistake, so I didn't contact either of these individuals. I wrote to Cristobal Rivas and I was like, could you please check my work? What's going on here? Because he had also asked me a similar question to this long before I read this paper. And we got talking, and actually this is an instance of a very specific phenomenon. So let's call this a corollary. And the theorem is, now we understand actually exactly what it means to have isolated points. So the space of orders on let me phrase it this way. If you give me a group and a circular order, this is isolated if and only if the associated action has a strong rigidity property. Okay, in the sense of topological dynamics. So let me tell you what I mean by strong rigidity. Okay, it should mean that if you perturb this a little bit, you're only changing it basically by a conjugacy. Okay, small perturbations are trivial deformations. Okay, so strong rigidity means that there exists a neighborhood, U of your action in the space of all such. Okay, so that if you take another action in this neighborhood, okay, there is some map of the circle. Okay, I'll leave a space for the conditions this satisfies. The map is going to be continuous and nice in various ways. but such that it intertwines the two actions. So if I do H followed by row C, this is the same thing as row followed by H. I got, yes. I had to think because actually the condition is not symmetric. It's a little tricky. And my H is required to be continuous. All the usual things, degree 1. It's monotone in the sense that it weakly preserves the order of points. So it's allowed to collapse an interval to a point, but not to kind of double back on itself a bunch of times. And row C came along with a special base point. What did I call it? XC. It fixes this special point. Okay, so this is a strong rigidity up to semi-conjugacy condition. So the proof of this has a bunch of ingredients, and I will tell you about almost none of them. One direction is not so bad, and it uses this continuity lemma to go this way. To go the other way requires a bunch of understanding of what these row C's particularly look at. We use some of the machinery that comes out of a proof of Margulis's kind of Tietz alternative for homeomorphisms of the circle that lets you find free groups. There's a bunch going on. So rather than sort of mire you in the details, I want to just give you an example of an isolated circular order on here. The sort of the thing that kicked off this whole, oh no, there's a counterexample, what's the phenomenon underneath this? Because it's also indicative of a bunch of unanswered future questions. Okay, so no proof of theorem. Instead, let's explore a specific example. Okay, the example really kind of tells you how you get from this theorem to this consequence. Okay, so I'm going to very loosely use the theorem to produce an example of one isolated circular order on a free group. And so one way I can specify a circular order on a group, remember, I just erased it. There was this construction where if I have a group acting on the circle and I have a point with trivial stabilizer, I can just look at its orbit and sort of look at the order of points there. So to produce an isolated circular order on the free group, I actually just have to produce an action and a point with trivial stabilizer. Okay, so I'm going to produce this example via defining so let's say my free group is generated by two homeomorphisms. I'll use colors for these, say A and B. I have to tell you what these do to the circle, and there's an example we all know and love. Whether you do low-dimensional topology or geometric group theory or anything like this. If I take A to have a source sink dynamics, where I'll take the complement of this interval into this interval. Okay, so the image of this point under A will be that one, and the image of this point under A will be that one, and I'll like stretch. So this is what A is doing. Okay, and I take two other intervals, and I require B to take the complement of this one. I stretch these points out and contract this so that B is doing this. The ping pong lemma which you should look up if you haven't seen it ever, is the statement that these two generate a free group. And actually, if you've ever proved this as a little exercise, you can show that if I take some point that's not in any of these intervals, say this one here, this point has trivial stabilizer. Okay. Actually, the proof of this is like an induction on word length in your group. If A takes it here, B takes it there, A followed by B will take it here. You just check cleverly that for any word of any length, it never comes back to itself. So this has trivial stabilizer. So we get circular order on the free group. All right. Now I will wave my hands in the direction of this theorem and say, well, look at this action has a strong rigidity looking property. If I change what A does a little bit, it'll, I perturb this a bit, it'll still take the complement of an interval here into the complement of an interval here. And B also will take the complement of an interval here into a complement of an interval here. They have, if you like fancy words and you do smooth dynamics, these kind of have hyperbolic dynamics, and that's a stable phenomenon. Okay. Okay. This action is stable under perturbations. Okay. So the theorem should imply, so stable or rigid. So the theorem will imply that this circular order is isolated. Okay. All right, so unfortunately, well, I did tell you a true statement. The circular order you get here is isolated. The theorem is true. This action is stable under perturbations. If you change it a bit, you get something that is semi-conjugate. Okay, but there's something missing from here. There's a little detail that I overlooked. Okay, and that's really level 2 talk to be done in a second hour, perhaps later tonight if you want to talk to me forever. But instead, I'll just tell you why this is what's missing here. And this looked too easy. How did we publish a paper out of this? Let me tell you that actually there's some wonderful, it's a much richer. Okay, so there's some hidden difficulties or interesting parts. Let's say subtleties. All right, so there was nothing really special about 2 generators to let me draw this picture, but alas, if you use the 3 generated subgroup, free group, this has no isolated points. Okay, so something in this theorem implies this is actually kind of fundamentally non-applicable to this example. In fact, this, things got so weird that a year after this theorem, we finally figured out what was going on with this example. And with an ever-increasing number of authors, now with Michele Triestino, we sort of figured out what was going on. Just for free groups, you have an isolated circular order. Okay. If and only if the number of free generators is even. Okay, So that's there, and there's a kind of a purely topological sort of combinatorial reason for this. Okay. So, but never fear, this was not a waste of your time. This is morally true in what's going on. It's just an interesting and very subtle phenomenon to work with. And so as a result, I hope this is evidence that this picture, this correspondence, using dynamical properties to answer algebraic questions, or hopefully eventually using algebraic structures to tell us something about dynamics and spaces of actions, is something that I believe is still a promising program, but seeing as we're still working out the details of what's up with free groups, something that I think will pay out only long term over the future. But that's a great place to end. Thank you very much.